Welcome. My name is Hubert Savenije and I'm a hydrologist. Hydrology is the science of water. It tries to describe and understand how water moves over and through the earth, and to find out what the physical processes are that drive the movement of water. More simply, you could say that hydrology is the science of the origin and fate of water on earth. But if you ask me, I would just say that hydrology is beautiful, even if it rains, or especially when it rains. Because everything we do, and because everything living on Earth depends on water, there are large and important scientific questions that demand our attention. Such as, where does the water come from? How much water is there available for the development, for feeding hungry mouths, and for a healthy environment? How can we better protect ourselves from water threats, such as floods and droughts? How can we maintain a healthy environment in a rapidly developing world? How does climate change propagate into the hydrological behavior and water resources availability? In which way do we, as human beings, influence the hydrology? And is there an interaction? And many people, particularly politicians, want us to tell when we can expect a flood. But that, unfortunately, is a question we cannot answer. We can communicate the probability of an extreme event to occur, but not easily the moment when it will occur. Prediction is difficult, in particular when it relates to the future. The question, where the water comes from, has inspired the great philosophers. The early Greek philosophers indeed believed that river water and groundwater were fed by rain, but they also liked to compare the earth to the human body. Leonardo da Vinci, whom we all know as the painter of the Mona Lisa, was not only a great artist, he was also an engineer, a writer, and a scientist. Leonardo wanted to understand what he painted. To be able to paint water and clouds realistically, he tried to better understand how it behaved. He developed instruments and devices to measure flow velocity, wind velocity, air humidity, etc. And he came to incredibly accurate insights. He even designed sluices, sluice gates, that are still in use in the Netherlands.
Look at that, they are just like Leonardo's drawings.
However, he respected the classical ideas of Plato so much that he thought that water was pumped through the earth in an analogy to the human body. And he thought that seawater was pumped through the earth to appear again on the top of mountains. It was more than 100 years later till the Frenchman Perrault could demonstrate that precipitation was sufficient to maintain the flow of the river Seine, which was a revolutionary idea, because the famous English scientist Halley, the one from the comet, he still believed that much of the river water originated in caves where moist air condensed against the cold mountain rock. The world's water resides in a system of interacting stocks and fluxes. Stocks are represented by boxes and fluxes by arrows. These boxes and arrows have very different sizes and magnitudes. By far the largest stock of water is in the oceans and seas, but this water is saline. The largest stock of fresh water is in the polar ice. But this is hardly accessible. And then there is a huge stock of water deep under the ground in large alluvial plains and even under the Sahara Desert. But this water is often fossil, not being replenished at the human timescale. The only sustainable stocks of water are the amounts that are regularly renewed. And these stocks generally lie close to the surface. We have come to indicate these stocks and fluxes by the colors blue and green. We distinguish the light blue water, which we can see on the surface, from the deep blue water, which feeds the surface water from underground. An equally large resource is the green water, which is a term coined by Professor Malin Valkenmark. And this is the water stored in the soil and used by plants to produce biomass. This is the water that feeds the world population with its agricultural products and which sustains our biomass-based economies. Part of the precipitation does not become blue or green, but evaporates back to the atmosphere directly. I named this white water. Here we see an overview of the magnitudes of these stocks and fluxes expressed per unit surface area. They are approximate values, but they clearly show that some fluxes are very large, for instance, the atmospheric flux, and some are very small, like the deep blue. Conversely, we see very large stocks, like the oceans, whereas some are very small, the white stock, for instance. The right column shows the ratio between the stocks and the fluxes, which represents the residence time. Let's look at these balances in an analytical way. The water balance is the most basic equation in hydrology. It implies conservation of mass. It shows that if there is an imbalance between inflow and outflow, that there then should be an increase of the storage over time. Or the time derivative of the storage is the difference between the inflow and the outflow. In hydrology, the inflow can be an inflow of water, but also precipitation on a surface. The outflow can be the river discharge, but also the evaporation from the surface. An interesting property of such water balance systems is that if we divide the storage by the outflow, we obtain a number with a time dimension. This number represents the average time that a water particle resides in the stock. More correctly, it is to say that this ratio of stock to flux is the time scale of the process. If we now look again at our global water resources table, then we see that the oceans have the largest residence time. Not surprising, a water particle, once it ends up in the ocean, has to wait on average 28,000 years before it may again travel to the land. In the atmosphere, however, a water particle resides only a few weeks on average. And thanks to the storage in the root zone of plants, they can survive half a year without rainfall on average. You may wonder why the flux from land to ocean through the rivers is 310 millimeters per annum, while the flux from ocean to land through the atmosphere is only 130 millimeters per annum. How come these numbers are not equal? Shouldn't they be the same? Of course, they are the same. We only have to multiply them by the right surface area. Because if we look at this picture, then on average, the fluxes A and Q should be equal and opposed. Otherwise, the storage in the ocean would either increase or decrease over time without end. You may be wondering what happens with the moisture you exhale.
I'm exhaling water. I wonder where the evaporation goes.
Does the moisture we exhale fall back as precipitation, or does it flow back to the ocean through the air? If we look at the global water balance again, then we see that it rains 720 millimeters per annum on Earth, while the net atmospheric influx from the ocean is only 310 millimeters per annum, a factor 2.3 different. In fact, a substantial part of the precipitation finds its origin in terrestrial evaporation. If we equate the terrestrial precipitation to 100%, then 40% of this water comes from terrestrial evaporation. Just look at the picture. Of the 100% precipitation, about 70% evaporates. A bit more than half of it returns on land, and the rest flows back to the ocean through the atmosphere. But it depends strongly on where you are on Earth. This is the paper by Ruud van der End, which describes this process in detail and also presents the figures. As a result of the dominating westerly winds on the northern hemisphere, exhaling moisture in the Netherlands here is likely to end up in China. But exhaling moisture in China is likely to end up in the Pacific Ocean. Here we see in red the parts of the world where the precipitation largely consists of recycled moisture. We see that China and West Africa strongly depend on recycled moisture. But where did this moisture come from? Here we see in red the reverse. Red are the source areas where the chance of evaporation ending up on land is larger than 60%. These are the areas where land evaporation has a significant influence on precipitation. So the Amazon forest in South America, the Great Lakes area in Africa, and Eastern Europe are very important source areas to sustain continental rainfall. And land use changes in these areas may have unexpected consequences downwind. Although global hydrology is extremely relevant for the analysis of human impacts on the planet, the natural limits of a hydrological system are much smaller. The natural boundary of a hydrological system is the watershed, catchment or river basin, in increasing order of size. This is because precipitation falling on a catchment has only two ways out: discharge through the outfall or evaporation back into the atmosphere.
So this is where it all drains out.
There is no other inflow assumed to be there than the precipitation. So the water balance reads that the change of storage over time equals the rainfall minus the evaporation minus the runoff through the outfall. Of course, all terms in the equation need to have the same dimensions. So if we express precipitation and evaporation in a length over time, then they have to be multiplied by the size of the catchment area. But we could also express all terms. We could express all terms in length over time. And in that case, the discharge and the storage need to be expressed per unit area. But is the water divide always a real divide? not all runoff is generated over the surface. A considerable part flows to the river through the groundwater. And because of the sometimes complex geology, the topographic divide and the groundwater divide do not always have to coincide, particularly in karstic or mountainous environments. This can lead to substantial errors if one tries to close the water budget. Here we see the water budgets of some of the major river basins of the world. We see that they differ in size, the Mississippi and the Ob being among the largest, and the Rhine being relatively small. We also see that the precipitation varies from 1,500 millimeters per annum in the Mekong to only 220 millimeters in the Nile. The evaporation from a catchment, of course, is always smaller than the precipitation, because in the catchment the precipitation is the only inflow. But the proportion of evaporation to rainfall varies a lot between catchments. In the Nile, the Zambezi and the Mississippi, containing substantial semi-arid parts, the evaporation is more than 80% of the precipitation. But in more humid climates, particularly the Orinoco, the evaporation is only 30% of the precipitation. Of course, the remainder is the runoff. And the Orinoco, where 30% of the precipitation evaporates, hence has a runoff ratio of 70%. The Orinoco drains essentially tropical rainforest. Therefore, it is interesting to see that a completely different catchment that also generates a lot of runoff, 60% of the precipitation, is a catchment in cold Siberia. Both have insufficient solar energy to evaporate most of the precipitation. The Orinoco, because it rains so much. The Ob, because there's insufficient solar energy. So different regions and different landscapes behave very differently all over the world. Hydrology is the science that wants to describe and understand this behavior. The landscape reflects this behavior. And if we read the landscape well, we can learn a lot more about its properties and dynamics. I hope you enjoyed this part of the course. And remember, hydrology is the basis of all other water-related disciplines and of the management of our resources.